Okay, so there is a couple of miscellaneous examples here as well. Let's go through them one by one. Miscellaneous examples. That is example number 10. Example number 10, find the term independent of x in the expansion of, you want to find the term independent of x. Independent of x in the expansion of three halves times x squared minus 1/3 1/3x whole raised to the power 6. Okay. Now to find the term independent of x, essentially you have to look for the term. Basically the term becomes independent of x when basically the general term of this expansion is basically t of r plus 1, which is equal to n combination r, which is the coefficient which doesn't contain any x or anything. The variable is not there. Then you have a raised to the power n minus r and b raised to the power r. These two contain x because you have the x over here in a, and you have in b you have the x, right? Okay, so now I was speculating about the solution here, but well, the solution is simple, meaning that you can say that in this particular case t of r plus 1, which is the general term of this expansion, is equal to n, which is 6 combination r, and then you have a raised to the power n minus r, which is 3 halves times x squared raised to the power 6 minus r. And then you have basically, you can write this as, you can say that basically then you have negative 1/3x raised to the power r, which is r. And then you can write this as 6 combination r, 3 halves raised to the power 6 minus r times x squared raised to the power 6 minus r, negative 1 raised to the power r, 1/3 raised to the power r, and 1/x raised to the power r, right? Which means that then you can write this as basically 6 combination r. So you have basically 3 halves. So this is the same thing as, you can write it as 3 halves raised to the power 6 minus r. Then you have 1/3 raised to the power r, 1/3 raised to the power r, and you have negative 1 raised to the power r. So this is taken care of. And this basically 3 halves raised to the power 6 minus r, 1/3 raised to the power r, negative 1 raised to the power r, and the only thing that here remains is basically these two terms that remain the x, that contain the x. And over here you have x squared raised to the power 6 minus r, which is basically x raised to the power 12 minus 12 minus 2r, right? And then you divide that by x raised to the power r, x raised to the power r, right? So now these two are also taken care of, right? Now what you can do is that of course you can simplify this part. Now these parts are not important because they don't contain the variable, and here we want to find the term that is independent of x, meaning that x should not be there, right? So basically x raised to the power 12 minus 2r divided by x raised to the power r is the same thing as x raised to the power 12 minus 2r minus r, which is equal to x raised to the power 12 negative 2r negative r negative 3r. So I can write this whole thing as 6 combination r, 3/2 raised to the power 6 minus r, 1/3 raised to the power r, negative 1 raised to the power r, x raised to the power 12 minus 3 times r. Now you know that if x is raised to the 0th power, then the whole thing becomes 1, and therefore x vanishes, right? Which means that the condition that we are looking for is actually is that 12 minus 3r is equal to 0, which means that negative 3r is equal to negative 12, 3r is equal to 12, and r is equal to 12 thirds, which is equal to 4. R should be equal to 4, right? And that is basically the fifth term. When r is equal to 4, that is basically t of 5, or basically the fifth term of the expansion and you can of course calculate that, meaning that you can write this as t of 5 over there. R is equal to 4, so you can write it as n, and basically in this case is equal to 6. So that's 6 combination, and r is equal to 4. Okay, so then you have here basically 6 combination 4. I did make some mistakes here. You have 6 combination 4, and a raised to the power a over here is basically, what is a? So a is 3/2 x squared, is 3/2 x squared raised to the power 6 minus 4 is equal to 2. And basically then you have b, which is basically negative 1 over 3x, negative 1 over 3x raised to the power 4, which is the same thing as 6 combination 4, 3/2 raised to the power 2, and 3/2 raised to the power 2, negative 1/3 raised to the power 4, and then you have basically x raised to the x squared raised to the power 2, 1 over x raised to the power 1 over x raised to the power 4, which is equal to 6 combination 4. So that is basically 3 raised to the power 2 over 2 raised to the power 2 times 1 over 3 raised to the power 4, right? And then you have x raised to the power 4 times 1 over x raised to the power 4. So you can cancel these two out. 3 raised to the power 2, 3 raised to the power 2 here. So you get basically 6 combination 4 over basically this. You'll get 6 combination 4 over 2 squared times 3 squared. Now 6 combination 4 is the same thing as 6 factorial over 4 factorial times 2 factorial, which is the same thing as basically 4 factorial times 5 times 6, 4 factorial times 2, and then you have 2 and 3 times 5 is equal to 15, so that's 15 over basically 4 times 9 is equal to 36, which is the same thing as divide by 3, you'll get 5, divide by 3, you'll get 12, that's 5 over 12. That's basically the term that is independent of x. Now, the next question that we have is question number 11. The next question is question number 11. So we have, if the coefficients of a raised to the power r minus 1, a raised to the power r, and a raised to the power r plus 1 in the expansion of 1 plus a raised to the power n are in arithmetic progression, prove that that is the case. So, example number 11 is if the coefficients of a raised to the power r minus 1, a raised to the power r, and a raised to the power r plus 1 are in the expansion of 1 plus a raised to the power n are in arithmetic progression. In arithmetic progression, prove that n squared minus n times 4r plus 1 plus 4r squared minus 2, 4r squared minus 2 is equal to 0. So the coefficients of a raised to the power n r minus 1, a raised to the power r, a raised to the power r plus 1. So, okay, so let me see. Okay, so now in order to solve this problem, I already did solve this problem once. There was a slight mistake in the end, which, as I trace now back, is due to some steps that I might have made a mistake somewhere over here or somewhere like that, and as a result, what I got over here in the algebra is not really right. But now that's not really the point. The point is that solving this kind of problem is really pointless. I mean, it's a lot of work, and you're proving something that you'll never actually get to use anywhere. But the point here is that maybe, I don't know, maybe you will be able to use it. Maybe basically you will use it in some examination and pass some examination using this, which would be, of course, a good thing, right? Moreover, now let me first erase this thing, and then we will get to the rest of the things. Okay, so okay, now if I Okay, so the point of this exercise, as I was saying, is basically, first of all, it might, I don't know about your examinations, you might be required to write this in an examination, and so you will get some points for this exercise, which would be, of course, a good thing. The second thing is that you will learn a couple of things along the way, but essentially what you will prove in this problem is pointless. I mean, there is no point in proving such a thing that, for example, if although you might actually be able to use that as well, because if you can prove that basically the coefficients of these three terms in this expansion are in arithmetic progression, then basically this relationship exists between n and r, then you might be able to use it somewhere. Who knows? But well, as far as we know, it's pointless, really. Now, the way that you can solve this problem is that, first of all, you need to know the coefficients of these three expressions. The expressions are basically, this is the solution. The expressions are a raised to the power basically r minus 1, and a raised to the power r, and a raised to the power r plus 1, right? Now, in the expansion of basically a plus b raised to the power n, the general term, which is t of r plus 1, is equal to n combination 0, a raised to the n combination r, a raised to the power n minus r, b raised to the power r, right? Which means that then in the expansion of basically 1 plus a raised to the power n, the general term would be basically t of r plus 1, which is equal to basically we are looking at 1 plus a raised to the power n, so that's n combination basically r at t of r plus 1, r would be 1 less than the term number, which would be r, n combination r, a in this case is 1 raised to the power n minus r, and b raised to the power r, so a raised to the power r, right? Which is the same thing as n combination r. This is just 1 times a raised to the power r. So that is t of r plus 1 in the expansion of of 1 plus a raised to the power n. So you can see that a raised to the power r occurs in t of r plus 1, right? So let's go back a term, and let's write the term. Let's write out the term t of r basically, right? So t of r therefore would be equal to n combination 1 less than this, so r minus 1, 1 raised to the power n minus r plus 1, and a raised to the power r minus 1. So that and that is basically the same thing as n combination r minus 1, a raised to the power r minus 1. That is T of R. That is T of R. And you can see that A of R minus 1 occurs in T of R. Occurs in T of R. So we have now gotten basically A of A raised to power R minus 1. We have gotten A raised to power R, so we need to get this one as well. And so from this, if I go back, if I go one term forward, I will get T of basically R plus 2. R plus 2 is equal to n combination, basically 1 less than this would be R minus R plus 1. 1 raised to the power n minus R minus 1, and A raised to the power R plus 1, which is the same thing as basically n combination R plus 1, A raised to the power R plus 1, and that is basically T of R plus 2. T of R plus 2. And that's basically the three terms that we were looking for. So you can see that the coefficient over here is n combination R, the coefficient here is n combination R minus 1, and the coefficient over here is n combination R plus 1. And we said that the coefficient of the three terms in the same order are in arithmetic progression. Now the coefficient of A raised to power R minus 1 is basically this coefficient here. So that means that then I can say that this coefficient, which is n combination R minus 1, and then the next term would be basically A raised to the power R, so the coefficient is n combination R, and then the next one would be n combination R plus 1. So these are in arithmetic progression. These coefficients are in arithmetic progression. These are in arithmetic progression. So now what that means is that what does it mean to say that, for example, three expressions or three terms or three whatever are in arithmetic progression? What that means is that basically, for example, suppose that you have 1, 2, 3, or let me give you another example. So suppose that you have 1 and 1 plus 2 is equal to 3, 3 plus 2 is equal to 5, 7, and so on and so forth. These numbers are said to be in arithmetic progression because this number over here, 3, can be written as 1 plus 2. 1 plus 2. This number over here can be written as 3 plus 2. 3 plus 2. This number over here can be written as 5 plus 2. That means that any of these numbers can be written as the previous number plus a 2. So this 2 is called the common difference. And well, the relationship between any three terms in an arithmetic progression is that, for example, if you think about, for example, these three numbers that are in the arithmetic progression, I can write 5 is equal to basically 3 plus 7, and then multiply 2 by 5. 2 times 5 is equal to 10. 3 plus 7 is equal to 10. If I continue the same arithmetic progression, 1, 3, 5, 7, 9, 11, 13, 15, and so on and so forth, and take any three consecutive terms, for example, 11, 13, and 15. Again, I can write the middle number, the number in the middle. I can write 13 is equal to 11 plus 15, and multiply this by 2. 26 is equal to 26, right? Which means that if these three terms are in arithmetic progression, I can write basically this term or this coefficient 2 times n combination R is the same thing as n combination r minus 1 plus n combination r plus 1. Or in other words, I can write basically n combination r minus 1, n combination r minus 1. This is supposed to be minus 1. Or in other words, I can write n combination r minus 1 plus n combination r plus 1 is the same thing as 2 times n combination r. That's basically the relationship that we have in this particular case between these three basically coefficients. Okay, so now basically we can write this expression as basically n factorial n minus r plus 1 factorial, and you need to be careful not to make any mistakes here, meaning that, for example, here you will get n minus r minus 1 factorial, which is the same thing as n minus r plus 1 factorial, which is basically what I have written over here. So if you make one mistake, then the whole thing basically is not going to be solved anymore. Of course, you know that already, but and then you have r minus 1 factorial, and then after that you have basically n factorial over n minus r plus 1 factorial, which is equal to n minus r minus 1 factorial. So you can write that as n minus r minus 1 factorial and r plus 1 factorial. And then that you can write as basically 2 times basically n factorial over n minus r factorial times r factorial, right? Now what you can do, the next step is that you can divide essentially you can basically all of the n factorials you can basically cancel out from these numerators, although you need to be careful, meaning that, for example, you have an n factorial here, n factorial here. So from this side of the equation, I take an n factorial out, and then I write that as, for example, 1 over this expression plus 1 over this expression, whatever that might be, right? Plus 2 times, basically 2 times n factorial divided by whatever I have over here. And then I get the 1 over here and n factorial here, n factorial here, then both of these is equal to. Both of these are in the denominator. I cancel them out and I'll get a 1 over here, and that's how you cancel them out. Otherwise, since these are added together, you don't want to make unnecessary mistake there, right? So that means that then I can cancel this out, write it as 1, cancel this out, write it as 1, and cancel this out, write it as 1. Then about these denominators, you need to make a couple of arrangements so that this thing basically works, right? First of all, you need to write this r minus 1 factorial. You don't need to do anything to that. And I'm saying that only because they have not done anything to that. Otherwise, I would say that you would have to do this or that. And that's only based on this situation, of course. In different situations, you would do different things, of course. And r, basically n minus r plus 1 factorial. You see over here n minus r plus 1 factorial. Because you don't want to confuse yourself, you can write that as n minus r minus 1 whole factorial, I suppose, n minus r plus 1. So you can write it this way. You can write it as n minus r minus 1 factorial. And then you can write this as essentially you can write that as 1 times 2 times 3 times all the way up to basically this would be the last term, so n minus r minus 1, right? Now the term that comes before that is, to get the term that comes before this, you need to basically, for example, use some model. For example, n factorial. N factorial is the same thing as, this is something easy that you can always remember. So that is 1 times 2 times 3 times basically all the way up to n. And the term that naturally comes before n is n minus 1. That you already know. The term that comes before that is n minus 2. The term that comes before that is n minus 3, and so on and so forth, right? Now, if you pay attention here, you can write this as n minus 0, and then as you, and please note that this is n minus something, and so on and so forth. This is not plus something. That would be different, right? So, since when you have n minus something, so as you can see, to get to the term before this term, I'm adding 1 to this number, and ignoring the sign. I'm not touching the sign. I'm just adding 1 to the 0. 1 plus 0 is equal to 1. 1 plus 1 is equal to 2. 1 plus 2 is equal to 3, and so on and so forth. So that means that over here, I can do the exact same thing to get to the term before this, which means that I can write basically adding 1 to r minus 1 would give me r, so that would be n minus r, right? And adding 1 again to r would give me n minus r plus 1. And of course, I have to write that in a pair of parentheses, otherwise that would be wrong, meaning that would not be the term before that. And so on and so forth. So that means that basically then I can write n minus r plus 1 factorial, which is basically what we had over here. I can write it as n minus r minus 1 whole factorial, and that would be the same thing as basically n minus r plus 1 times n minus r times n minus r minus 1. Now, what you can do here, basically in the book, they have written these in the other form, which always confuses me. So I always write my things this way if I'm supposed to understand them. So this you can write n minus r minus 1. This you can write n minus r. And this you can write as n minus r plus 1, right? And that's basically times 1 and so on and so forth all the way up to 1. Now, if you have something like, for example, if you have something like n factorial, which is 1 times 2 times 3 times all the way up to n, the term before that, as we argued before, is n minus 1. The term before that is n minus 2. The term before that is n minus 3, and so on and so forth. Now, as you can see, for example, this part from here, from 1 all the way up to n minus 1, I can write it as n minus 3. I can write it as n minus 3 factorial. And then, based on that, I can say that n factorial is the same thing as n minus 3 factorial times these three things, n minus 2 times n minus 1 times n, right? That I can write based on what I did here. And so you can do the same thing over here, meaning that basically n minus 1 plus 1 factorial, you can write it as n minus r plus n minus r plus 1 factorial. You can write it as n minus r minus 1. You can write this part from 1 all the way up to this part. You can write it as n minus r minus 1 factorial times n minus r times n minus r plus 1, right? Times n minus r plus 1. And that would be basically this expression that we were looking at. So n minus r minus 1 factorial times n minus r times n minus r plus 1. So that is the first part here. That is the first part here. So let me check actually to see if that's correct. And then, so here we have n minus r plus 1 times n minus r times n minus r minus 1 factorial. That is absolutely correct. Okay, so this is about this first part over here. So we will write this part, this part over here, we will write it as this, and then basically n minus r minus 1 factorial, and so r plus 1 factorial over here. We don't have to do anything about this, but essentially r plus 1 factorial, you can write it as basically 1 times 2 times 3 all the way up to r plus 1, right? R plus 1. And then the term that comes before that is, of course, basically the term that comes before this is r, and the terms that comes before this is r minus 1, right? So this becomes basically r plus 1, r minus 1. So then you can write all of these terms as r minus 1 factorial, and therefore you will be able to write r plus 1 factorial as basically this whole thing, which is r minus 1 factorial times these two, r times r times r plus 1. And therefore you will be able to write this as, you will be able to write r plus 1 factorial as r minus 1 factorial times r plus 1. That is basically the second part that you need to note here. The third part that you need to note here is basically these two parts, n minus r factorial, no, I'm sorry. Yes, these two parts that you will write as, so n minus r factorial, you can write it as basically that's the same thing as 1 times 2 times 3 times all the way up to basically n minus r, and then the term that comes before this is of course n minus, you have to add 1 to this term here, so n minus basically r plus 1, right? And which becomes the same thing as basically n minus r minus 1 times n minus r. And then all of these things, all of these terms all the way up to here, you can write as n minus r minus 1 whole factorial, and so the n minus r whole factorial is the same thing as n minus r minus 1 factorial times n minus r, right? N minus r minus 1 factorial times n minus r, and therefore you will be able to write basically n minus r factorial as basically n minus r times n minus r minus 1 whole factorial. That's another part that we have here. And r factorial that we have here, is the same thing as basically r factorial, which is 1 times 2 times 3 times all the way up to r. The term before that becomes r minus 1, and therefore all of these terms we can write as r minus 1 factorial times and so r factorial would be equal to r times r minus 1 factorial. R times r minus 1 factorial. Now with all of these, we can rewrite those fractions. So to rewrite those fractions, I can write this as 1 over, now n minus r plus 1 factorial, I can write it as n minus r minus 1 factorial, times n minus r times n minus r plus 1, right? That I can write. And r minus 1 factorial, I will write it as r minus 1 factorial. So that is basically one part. And then over here I have 1, and then I have r plus 1 factorial, and so I write n minus r minus 1 factorial as it is, and r plus 1 factorial, I write it as r minus 1 factorial times r times r times r plus 1 times r plus 1 times r times r times r plus 1. And this fraction over here, I write it as basically 2 times basically 1 over, so we have n minus r factorial, which we can write as n minus r times n minus r minus 1 factorial, and r factorial we can write it as r times r minus 1 factorial. And so that way we have now rewritten all of the fractions. Now what you can do is that from these two fractions you can take, as you can see, n minus r minus 1 factorial, n minus 1 minus r minus 1 factorial, these are common in the denominator. And r minus 1 factorial are again common. And then over here you have basically, you can take these out, meaning that you can write basically 1 over n minus r minus 1 factorial times r minus 1 factorial, and times basically 1 over n minus r times n minus r plus 1 plus basically plus 1 over r times r plus 1, right? Plus r times r plus 1. And therefore you have this part we have over here, and then you have basically this part, which is equal to 2 times, you can write the 2 in the numerator, and you have n minus r times n minus r minus 1 factorial times r minus 1 factorial, and then you can basically simplify these in the denominator. R minus 1 factorial, for example, r minus 1 factorial, you can simplify them, and n minus r minus 1 factorial and n minus r minus 1 factorial, you can simplify here, which means that you will be left with basically 1 over n minus r times n minus r plus 1, and then add to that basically 1 over r times r plus 1, and that is equal to 2 over basically r times n minus r, right? Yeah. So I have 1 over n minus r plus 1 times n minus r plus 1 over r times r plus 1 is equal to 2 over r times n minus r. That's basically what we have here. Then you can basically take an LCM here of n minus r times n minus r plus 1 times r plus 1, and just add these two together, meaning that if you divide, you will get these two cancelled out, and then you'll have r times r plus 1, plus divide these two, you'll get these two cancelled out, you'll have n minus r times n minus r plus 1, right? And that is equal to 2 divided by r times n minus r. And then you will be able to cancel these out, and n minus r and n minus r you can cancel out, which means that then basically r times r plus 1, which means that r times r plus 1 plus n minus r times n minus r plus 1 is equal to 2 times r plus 1 times n minus r plus 1, right? Or you can rewrite this as basically r squared plus r plus basically multiplying n by this, you'll get n squared minus nr plus n, multiplying negative r by this, you'll get negative nr, positive r squared negative r is equal to 2 times basically nr minus r squared plus r plus n minus r plus 1, which is the same thing as now r squared, and r squared is equal to 2 times r squared, and n squared, you have only one n squared here, and you have r and negative r, you can cancel them out here, and negative nr, that's negative 2 times nr, right? And then you have an n over here, and then over here you have basically r and r you can cancel out, you have nr, so you can write this as is equal to 2 times nr minus 2 times r squared plus 2 times n plus 2, right? Now you have basically, and then bringing everything to one side of the equation, you get 2r squared plus n squared minus 2 times nr plus n minus 2 times nr plus 2 times r squared minus 2n minus 2 is equal to 0. And then you have 2 times r squared plus 2 times r squared is equal to 4 times r squared, and plus n squared. Negative 2 times nr, negative 2 times nr is equal to negative 4 times nr. Negative 4 times nr, and this we have already written. Now we have an n over here, negative 2n, that's negative n minus 2 is equal to 0. Which means that then I will be able to write this as n squared plus 4 times minus 4 times nr. I can write this as n squared minus 4 times nr, and minus n plus 4 times r squared minus 2 is equal to 0. And therefore from this you can write this as n squared. From this you can take an n out, so minus n times 4 times r minus plus 1, 4 times r plus 1. And from this you can take it, well, you can just write it as 4 times r squared minus 2 is equal to 0. So n squared minus n times 4r plus 1 plus 4r squared minus 2 is equal to 0. And that's basically what we wanted to prove. Right? So that was question number 11. We have question number 12, 13, 14, 15, 16, 17, and that's the end of these questions. Okay, so that was question number 11. So I'll see you in the next video. Thank you.